Okay, so we spent the whole of last lesson differentiating this thing by first principles, and Ben has asked, okay, why do I not have dy dx here? Now, the problem is, in calculus and in your textbooks, right, the reason why they use so many different bits of notation is we already know two people who kind of contribute to this field, right? Well, what was one of them? Newton and Leibniz. There was another.
Usain Bolt.
Usain Bolt, yeah, speed guy. There was another guy. His name was
Flash.
And he came up with this notation here, f dash of x. Okay. So all of these actually mean the same thing. Okay. Let me just write down all of them really clearly. So we have dy dx, and the reason why we have dy dx is because we have the change in y over the change in x. That was understanding the limit definition we're using. The reason why we have f dash of x
Quicker?
is because, yeah, it's a bit quicker, but also remember, think about the benefit of understanding f of x. Using f of x, we could substitute, remember when we had to find f of x plus h?
100 into it or something.
Yeah, right, we could try interchangeably see what would happen when we change the x value. So f dash of x is useful, so when I substitute something in, I can see clearly what I'm actually doing. And, is there another one? Oh, yeah, so what Ben was asking, this guy here, it's sort of similar, but it's saying, I want to apply differentiation, okay? So it's very similar to this one, but if you imagine this guy as not a value, but as a kind of operation, right? Like plus or minus, right? I want to apply differentiation to whatever this guy is here, because really, this guy here says you're applying d dx to y, okay? And that's why we have dy dx, that's the derivative function. But really what it's saying is, let's apply this differentiation process.
So now you can apply to anything.
Right, so we're not just doing it to y, they're going to give me the function, and then I want to apply differentiation to it, okay? Let's look at an example of how this works. So I've got my y value here, and I want to find dy dx. The way I do that is, as you guys observed in the pattern, you take your power, and then what you're going to do is you're going to drop it down. Okay, you're going to drop it down in front of your original, and you're going to say, okay, I want to multiply them together. But this power now, I have to
Drop down as well.
right, I have to subtract 1 from that. So I'm going to get 2 to the minus 1, x to the power 2 minus 1, which is actually just 2 to the x. Right? And that confirms what we were looking at, right? I had a parabola, and when I applied the derivative function, I got the equation of
Right.
a
So
line.
it's just a shortcut.
Yeah, this is like a shortcut, right? But it's important when we're doing this, because anyone can look at this pattern and do it. It's important to remember what you're finding when you're using the derivative. It's a very powerful thing.
What do we
You're
find?
finding the gradient function over here. Right. Don't forget that. When you're finding the derivative, you're actually finding the equation of this graphic. Let's get going. Okay. Because doing
So
this
is that
will
all
be...
that question asks for? Is that?
Yeah, so when you want to differentiate something, all they're asking you to do is find dy dx, okay, or f dash x. However they write it, that's probably the best way for you to write it as well. So dy dx for this one,
Would it be 3? Is that it?
all we want to do here is realize, okay, I drop my power down,
3
and then I subtract the power by 1. So I've got 3 minus 1.
Only one.
Let's keep going, let's keep going. Now, the issue is when we get something like this, right? I know that y is equal, so I want to find dy dx. But there's already a number in front of that. Now the reason why I got you to write down this kind of complicated thing is... Sorry, right. You can see here, it's telling me, okay, every time I want to differentiate something, I reduce the power by 1. But if I already have a coefficient or a number in front of my term, what do I do with it?
Bang it.
Yeah, good point. I multiply it by what's already there. So I don't want to change anything else, but I do want to keep in mind that I still need to do something with this one. So what I would do is I would say, okay, let's drop the power down. And so I've got now 2 times 2 x to the 2 minus 1, which actually just gives me...
Wait, why are you timing?
Because he's given...
Because there's a number already there. There's
Is
already
that
a
the K
coefficient.
in that?
Yeah, right. Yeah, that's why I got you to write out this whole thing, even though it looks confusing.
Why do you use K?
So is it sort of
Ran out
like
of letters.
you just do what you
Could've
did
used that.
and then you times it by the number you
Exactly, right. So every time we differentiate something, we always have to drop the power, and we always have to subtract it by 1. But what's going to change is if there's any coefficients.
So
or numbers in front.
will the power be the thing that you times it by? So it's 2 there,
Yeah.
and you times it by 2?
Yeah, exactly. Yeah.
So that's what's 2x cubed,
Yeah.
times by 3.
Yeah, so let me just do 2x cubed up here. So I'll put it in V. If I applied dy dx to the one that Ben just said, so 2x cubed, what I would do is I would say, okay, I need to drop that power down.
So it'd be 2 times.
So I've got 3 times 2x to the 3 minus 1, which actually just gives me
That's easy.
3 times 2x squared, which equals to 6x.
So is that meant to be your...
The thing is though, year 11, when you're doing this,
You can easily make a mistake.
no, it's not that. When you're doing this, the reason why I got you to do first principles first is because you need to develop the understanding of what the derivative is. Without that, just doing these questions, anyone could do that. Maybe like a year 7 student could realize the pattern of just dropping it down and then ticking this off by 1.
Pretty easy.
But you need to remember what you're actually doing. This is giving you the derivative function, which you work so hard to try and understand. You've got these curves and these lines, and when you apply the derivative function, when you try and find the derivative, what you're finding is how the gradient is changing.
So
over
this
time.
is like a way quicker way of doing the...
It is.
So basically